Okay, so after much thrashing about and gnashing of teeth and a little bit of money, I think I now have a piece of software in a system where I can record some video of my screen and post it for you guys to be able to get some decent audiovisual lecture material. What I've got in front of you is a spreadsheet, which I'll post to Blackboard, that shows two distribution of normal frequency scores. So I've used some Microsoft Excel functions. You can sort of see those functions here. They're a little bit hard to read. Um, Let me make that one cell bigger. Okay. And then I'm using the F2 key to show you I'm using a built-in function for a normal distribution, and I'm telling it to use these two cells for the mean and standard deviation. I'm asking it not to give me a cumulative distribution, so that's how we got that. Okay, then I'll do Control Z to shrink the size back down. Right, so what we're often doing when we're trying to make statistical analysis is we're trying to tell whether or not some treatment, some intervention, some factor has an effect on a wide variety of people, subjects, instances. And because the things that we care about are often the result of lots of different factors, we often wind up with a normal distribution, a bell-shaped curve. And so in this case, what you can see here is I've got two curves, a green one and an orange one. And while it would be easy to tell that there's this difference if we have all of the subjects in the population and they're all being subjected to this treatment and we look before and after, we can easily visually see on a graph like this that it made a difference. But usually we're not dealing with all of the subjects, we're dealing with samples. And so if the sample is relatively small, in this case just two instances, then what we expect is that we're going to get scores that are going to be sometimes above, sometimes below the mean of this green population distribution's mean, but that the mean of our sample, that is, if we add those two scores together and divide by 2, that sample mean will also vary. I grab two new scores from the distribution and I'm going to wind up with a new sample, a new mean. And so this sample mean has its own distribution. And you'll notice that if there's a sample of size 1, that means we're just taking one score, the distribution is the same mean and shape as the population. Just focus on the green distribution for right now. If my sample is larger, like let's suppose I roll a die, sometimes I'm going to get a 1, sometimes I get a 2, 3, 4, 5, 6, a standard die. That distribution is uniform, meaning it's flat. But if I generate my scores by throwing 3 dice and adding them together, I can get scores as low as 3, that's 3 ones, as high as 18, that's 3 sixes. But on average, I'm going to get scores around 10.5. And sure enough, if you plot that frequency distribution, you have something that begins to approach a normal curve. So anytime we have a behavior, a personality trait, any feature that's the result of lots of different things being accumulated together, added up, the central limit theorem says we should expect to see that the distribution of that additive accumulation is normal in shape. And basically that's just saying it's less likely for us to get all things lining up in one direction or another. So it's less likely for us to get 3 ones than it is to get, a 1 and then a 5 and a 2. Any combination of those 3 dice rolls that winds up in the middle, there's lots of ways to get 10 or 11. There's only one way to get 3. That's to roll 3 ones. Okay, so when we have these distributions that are sampled and our sample sizes get larger, because the sample means tend to have less variability, as our sample sizes get larger and larger, this bottom distribution down here, the distribution of sample means, has less and less variability. In fact, it goes down, the variability goes down as the square root of the sample size. So a distribution with 100 sample scores drawn from it has a distribution of sample means that has 1/10 the variability of the original population. And you can already begin to see what this means. If I have a treatment that causes the population to shift, and I only sample a couple of scores, it's harder to see that because our sample means will be shifted over, but there's going to be a fair amount of overlap. And in fact, this number up here shows where the mean for that second population is. When we talk about effect size, we're talking about how big is this treatment or this intervention, how big is the effect. If the effect is on the order of, let's say, the standard deviation of the population, then there's a lot of overlap in these two populations. And so it's much harder to see with confidence that our effect made any difference. If you have something which has mild or modest effects, like Prozac, which has a relatively small effect size, then often people taking Prozac for a week or two, they don't even notice their symptoms have reduced. Now, if you ask their family members, often the family members can tell. But if we test enough people, then one of the things that happens is we begin to see this separation. It becomes more and more obvious as we have large clinical trials that there really is a difference. This sample mean for this larger sample is way over here compared to what we would expect from the population. All right, so this is the heart of a lot of our statistical tests, understanding this relationship between samples, the distribution of sample means, and the distribution of the population of scores. And so all of our tables and formulas and software is about, kind of automating this process. But at the heart of it is this ability to make a decision about whether or not our treatment, our intervention, our population is different.